So this work that is coming out from PNAS is actually work inspired by mussels, not this mussel, but mussels that you eat, the bivalves. And you might have seen it at the beach that they actually stick very tightly onto the rocks where they anchor. And so there's a material that actually is responsible for the stickiness and also have this protective behavior that helps it to self-heal itself when there's sand abrasion or when there are waves, hurting the integrity of the materials. And so it is the sort of combination of the natural biological system and the extension using a man-made design framework that allow us to get at the chemistry and the physics of what is necessary to make the materials that has the adhesiveness that we require, that has the strength, as well as has the capability of healing itself if some sort of wear and tear has occurred on the system.
What we use as a starting material comes from, as Ka Yee said, Phil Messersmith up at Northwestern, which is a polymer that they made that mimics the natural molecule in the mussel with its adhesive capacity. So we dissolve some of that in just water, and then to that also add a little bit of iron chloride, which is basically just bought from any chemical company, that we will also dissolve in some water. And those two solutions we will mix together, and then the final ingredient we will add is sodium hydroxide, which is basically just base. And we will add that basically just to increase the pH of the solution to initiate the cross-linking of the gel, which then initiates the unique self-healing mechanical properties. This is the polymer that is now dissolved in water, and I'm going to take a small volume of that and put it on the sheet. We're going to add a little bit of the iron chloride, which should then make the polymer bind the iron chloride. But since this is all at low pH, it's going to be green and still a fluid. You can see it's beginning to turn green, and the more we mix it, the more it binds. So the green color comes from the polymer binding the iron chloride. And this next step is when the magic happens. So this is where we really copied the mussel and realized that maybe what the mussel does is actually increase the pH of a polymer solution mixed with iron. And once it does that, the cross-linking happens. Well, it's still an untested model for the biological system, but we thought, well, we'll try it with this man-made system and see what happens. So I'm going to try to put the solutions next to each other first. See? As soon as they hit each other, you can actually see that right where those two fluid boundaries meet, the red gelation happens instantly. It's so fast that it basically just jams and locks. And so what we've been doing, instead of waiting, is basically just physically begin mixing. And I'll try to do it gently. But you can see basically everywhere where the pH increases, where you mix the sodium hydroxide into the green polymer iron solution, you get the gel formation happening. And you can see it's still sort of a very biphasic system at this point, because part of it is gel, part of it is still polymer iron chloride green solution. But if you just keep mixing and you're patient, you eventually get one cohesive gel. This is a piece of gel just like the one you just saw made, that has been sitting for a while and has relaxed a little bit. And as you can see, it looks like a droplet, but this is the one we just made. And you can see that one is still somewhat elastic because it's still relaxing basically. This one has had time to relax. Or when you look at it, it looks like a liquid, but as soon as you touch it, you can see it still has these jelly properties. And you can see because it's relaxed, it's sort of turned into this more somewhat fluid state. I'm just going to try to squeeze it flat and see what happens. So you can see we can obviously squeeze it, and there you can see the sort of dark red color even better. As you can see, it's sticky. So this is obviously a hydrophobic plastic material, but it sticks very, very well to that. And again, we can just, we can pick it back up, make it into a cohesive ball again, and keep playing with it.